Hello and welcome to another Zosin session. How about that? Bet you didn't expect that shit to happen, so we took a little bit of a break, but we're back. Champions of the arena. So, today I want to do something very simple, but at the same time, fun, right? So, simple but fun. Simple but fun. So let's take a look at the classical problem of, detecting that a particular rectangle intersects or overlaps a circle. Right, so let's define this stuff like that. So let's draw a rectangle, and here's a beautiful, beautiful rectangle. And let me save the color just in case, and let's take a look at the circle. Right, so there we go. So how can we detect this kind of situation? So the problem is very well known, and there is like a good solutions for that. But I wanted to explain this thing with a little bit of a visualization, right? And for the visualization today, I wanted to use something called Shadertoy, right? So Shadertoy is basically a website that allows you to write the GLSL shaders, the shaders of OpenGL, and then using WebGL, right? So WebGL is basically the bindings of OpenGL into the web. So you can do OpenGL in a browser using JavaScript. So using WebGL, it then compiles all of that and runs it on your GPU. So here is a very simple shader. I wonder if we can make it slightly bigger so we can see shit in this mist. Okay, I think we can see that. And there we go. So here's a simple shader, and it generates these beautiful, beautiful pictures. Isn't that cool? I think it's pretty goddamn cool. Look at that. Look at that beautiful shader. Oh my God. Anyway, so I want you to use this thing to visualize the problem and just like show how you can detect the rectangle overlapping the circle. So I suppose we could split this video into like two parts. The first part is going to be me coding the entire visualization. Right, it's not going to it's going to be too complicated, but I still want to explain everything that I do. And then using that visualization, I'm going to explain how you can detect programmatically that a rectangle intersects a circle. So maybe for the actual explanation, if you're only interested in detecting how to, if you're only interested in detecting whether a rectangle overlaps with the circle, maybe I'm going to put like some sort of a timestamp to like for you to jump when I finish the visualization part. So yeah, for those who's interested in the whole thing and especially interested in shaders, let's actually do a little bit of a shader coding. So in Shadertoy, you can only code the fragment shaders, right? There are different kinds of shaders of OpenGL. There is like a vertex shader, there are geometry shaders, there are tessellation shaders. I don't know what's the difference between tessellation and geometry. I know nothing about OpenGL. And there are fragment shaders. So the fragment shaders, they operate on sort of like each individual pixels, and they call them fragments. There's probably a good reason to call them fragments instead of pixels. So yeah, but I like to think about them as pixels, even though it's probably incorrect. And essentially a single shader is a single function that accepts a color. It accepts the coordinate of the pixels, right? So here's the coordinate of the pixels and outputs the color of that pixel. And you give that shader to the GPU, or specifically OpenGL, and OpenGL does some magic and just gives that to GPU. And then GPU sort of runs this function on each individual pixel coordinate simultaneously, computing the final image, right? So it's like requires a little bit of a paradigm shift, because usually you visualize by issuing explicit commands like draw a rectangle there or draw a circle there, and so on and so forth. But now you have to like switch your paradigm a little bit. Now you cannot say that. You're only given one pixel, right? You're only given a one pixel at a time, and you need to draw different shapes with that. How are you supposed to even draw different shapes with that if you only have a control over a single pixel? Well, one thing you can have is you can have like a global definition of the rectangle that is visible to all of the pixels. And then inside of the function, you can check whether the current pixel belongs to the rectangle or if it does not. if it belongs to the rectangle, that means the pixel is going to be colored one way, one color. If it's not, it's going to be colored a different color. So that's basically how you can draw simple shapes. The same you can do with the circles and stuff like that. So that's basically the idea of how you do graphics with fragment shaders. So with different shaders, you might do actually different things. With vertex shaders, it's a completely different story. In any case, so the coordinate of the pixel is located in the frag chord, right? So let's actually go ahead and maybe set the color of the entire thing to black. And let me remove everything, and maybe it would be nice to save the position to some sort of variable. So it's going to be frag coordinate, x, y, and there we go. So how can we define a rectangle? Let's define a rectangle as maybe position and a size of the rectangle, right? So this is going to be something like, well, I already took a P, so maybe we should rename it to something else. Okay, so this is going to be rect position, right? And rect position is going to be essentially somewhere at 100, 100. So this is where the rectangle is going to start. And this is going to be the size of the rectangle. So what I'm coding in right now, I'm not really coding in C, right? I'm coding in something called GLSL, which is like C, but it's a programming language that compiles to something that can run on your GPU. So if you want to learn more about GLSL, I recommend to just Google it up. So on the Kronos group, the group that is responsible for OpenGL standardization, there is like an article about what is GLSL. So it's a shading language for OpenGL. So, and yeah, that's pretty much it. So maybe I'm going to actually put that in the description. So I didn't put anything in the description so far yet. So I think the time has come to actually do that. On GLSL. And I think I would also like to put the link to the Shadertoy here in the description as well for people who wants to play with it. Shadertoy. So here is the link to the Shadertoy. There we go. So, and the GLSL has different types. It has built-in types of vectors, two-dimensional vectors, four-dimensional vectors, and four-dimensional vectors are usually used for special 3D math or for representing colors, right? So because the color usually has RGBA components, which is four-dimensional vector essentially. Right, so we defined position and the size. So, but it would be easier to actually have a representation of 2 points in the rectangle, right? Because then I can take the current pixel and check if it's between the components of these points, right? So let's actually do something like this. I'm going to define P1, which is the rectangle position itself, and then P2, which is the rectangle position plus the size. So, which actually kind of makes this entire thing a bit redundant. Maybe I'm gonna actually just inline everything in here, right? So this is gonna be that, and then P1 is gonna be something like this. So I'm gonna grab the size, and I wish I had like a better key bindings in here, but at least deleting a line works. I can do Ctrl-D and I can delete the line, which is already pretty convenient. Anyway, so here's 2 points, and what I need to do, I need to check if the current point P is between these 2 points. So we're going to start with X. P1 X less or equal than PX, and PX is less than equal P2X. And in that case, we can actually color the pixel with a completely different color. So let's actually color it with white. Right, so something like this, and maybe I'm going to actually first set, right, so I'm going to set the background color to black, and then if the X of the current pixel is between the boundaries, left and right boundaries of the rectangle, we're going to color everything white. And as you can see, it only works for X's, right? For Y, we don't check that yet. So we can quite easily add that too. So maybe I'm going to do something like, let me actually copy paste this entire thing. So it's going to be pretty straightforward, I think. So, and I'm going to replace all of that with Y. And there we go, we have a rectangle, and we can even change its like position. So let's actually maybe place it somewhere here, or maybe we can even change the size of this entire thing, and there we go. And there is a problem in here. When I scale the whole thing up, it stays the same size. It would be nice for this entire thing to scale with the resolution, but we can address that a little bit later. Right, we can address that a little bit later, I think. So we can draw rectangles, but I would like to actually maybe factor this entire thing out. I would like to have a function that sort of accepts a rectangle representation and a point representation and answers this simple question: does rectangle contains a particular point? So how can we represent a rectangle? Right, we could probably pass P1 and P2, which is probably fine, right? So yeah, let's actually go ahead and do that. So vector 2 P1, vector 2 P2, and vector 2 P. Right, there we go. So the first two arguments here, they represent the points, and then the point within which we're checking everything. All right, so, and we might actually take this entire condition in here and just factor it into this function, right? So we don't have to deal with this messy condition, and let's just do it something like this. So rect contains point, and we provide P1, P2, P, and there we go. Everything seems to be working. We can also try to change the color of the rectangle. For example, if we don't like the white color, we can put something like a red. Right, there we go. So now it is red. I can change things like that. So now it's green or blue. Well, you have to put one in here. There we go. So, but maybe for now, I'm gonna just keep it white. Right. Maybe blue. I actually kind of like blue. So let's keep it blue. There we go. So let's actually try to draw a circle. We can draw a circle in a very similar fashion, right? So we can have a function that basically answers the question: does circle contain a particular point, right? So, and how can we represent the circle? We can represent the circle as center plus its radius. So the center is going to be also two-dimensional thing. So here's the center. Then we can have a radius and then the point for which we're actually checking everything in here. So to check if a particular point is within the circle, what do? We find the distance between the center of the circle and the point, right? So yeah, so we can even visualize that super quick. Essentially something like this. And if the point is in here, so you find the distance, here is the distance. Is it less than the radius? If it's less than the radius, that means it's within the circle. If it's outside and bigger than the radius, that means it's outside. It's actually pretty straightforward to detect this kind of thing. Right, so let's go ahead and do that. So I'm going to subtract center from the point and find the length of it, right? And just check if it's less or equal than the radius. And this is the entire check, actually, right? This is the entire check. And now I can try to define a circle somehow. So let's have something like C. Where are we going to position our circle? Let's actually position it somewhere here. Right, and what kind of radius are we going to have? Let's say the radius is going to be 100. All of that can be adjusted like a little bit later. And if circle contain C, I want to call it contain C, but for some reason I just called it contain. If the circle contains the point, all right, so here's the center, here's the radius, and here is the point, right? We're gonna color it with a different color. So this is gonna be frag color vec4, and let's say that it's going to be green, I suppose, right? So this is gonna be green thingy, and there we go. And this entire thing didn't compile because I forgot a semicolon. Dimension mismatch. Oh, this one has to be float. Of course, the radius is not a two-dimensional vector, it is a scalar. There we go. So here is the circle. We can position that circle maybe in different places. I think it's too big. If you ask me, yeah, it's a little bit better. So yeah, so we can position it in different places, maybe somewhere here, maybe 350 and stuff like that. Yeah, that's pretty straightforward, right? So But what's interesting is that this is how we handle everything. So first we set the background color, right? I can set the background color to white, and this entire thing will become white, of course. Then we check if the current pixel is inside of the rectangle, and we reset the background to blue, to the color of the rectangle, and then we check again if it's within the circle. That means we reset to the circle. So a circle sort of like has a priority over a rectangle, right? So if we sort of place this a little bit in here, right, so it always obscures the rectangle, right? But if we change the order in which we check for these kind of things, and now the rectangle obscures the circle, right? I would like to be able to see how they overlap, so I don't really want them to obscure each other. So one thing we can do, and as you can see, here's the components. They're sort of independent, right? So what we can try to do, we can basically add the colors to each other, right? We can add the colors to each other. So to not oversaturate the alpha, I'm gonna just set the alpha to 0, and I think alpha in Shadertoy doesn't really mean anything, so it's totally fine. And there we go. So as you can see now, if they overlap, they create a cyan because their components combine, and we can see the actual intersection between them, which is rather convenient, right? Which is in fact rather convenient. And here is another interesting thing you can do in Shadertoy. You can actually accept user input. So one of the things we can have in here is the mouse position. So you can take the mouse position and just use it for whatever you want. For instance, let's say that the center of the circle is equal to the mouse position. So this is going to be I mouse XY, and now I can control it around. So easy. We already have pretty much enough visualization to demonstrate how you can detect that a circle intersect the rectangle, which is quite convenient, to be fair. So one thing I would like to actually fix is being able to, you know, scale it up, right? And the shapes also, and force the shapes to also scale up with the resolution of the screen. So as far as I know, we know the resolution of the screen at any time. So the resolution of the screen is actually given to us by Shadertoy. So if we take the point and divide it by I resolution, we effectively map the coordinates to we basically normalize it, right? So we make them be equal from 0 to 1. Okay, so let me actually maybe draw that. It's kind of difficult to explain this kind of thing. All right. So imagine that we have a particular screen with a particular dimension, like width and height, right? And you have a point in here, right? So which is x and y. If you take x and divide it by w, you will get a value essentially between 0 and 1, because x is always less than w. Right. So, and if you take y and divide it by height, you're always gonna get the value, you know, between 0 and 1, because y is always less than height. And that's effectively what we did in here. We took the position within the screen and we divided it by the resolution of the screen, and we got the coordinates in a normalized coordinate system from 0 to 1. Right. So we have now normalized coordinates. Once we have normalized coordinates, we can actually map those coordinates to whatever resolution we want, right? We can, for instance, say that our resolution is always going to be 1600 by 900, right? By 900. And no matter what's the current resolution of the screen, we always will try to remap everything to that specific resolution by first normalizing everything and then multiplying it by this entire resolution, right? So we're basically remapping to our own resolution, to the constant resolution, and we do not depend on the variable resolution. So if in here I now multiply it by vector 2 1600s. Is that how English people say? Yeah. So instead of saying 1600, English people like to say 1600s, right? Probably because it's shorter. So we don't usually do that in Russian language. And now if so as you can see, it already looks like it looked like when I actually scaled it up, right? So, but if I actually scale it up, the size is a little bit bigger. So it tries to maintain proportions relative to the size of the screen. So that's basically what we have in here. And because of that, we can now place those things in bigger coordinates. Let's actually place the rectangle somewhere here, and we can quite easily make it a little bit bigger. So maybe I'm going to multiply this entire thing by 2. Right, so yeah, maybe even by 3. Why not? Let's go crazy and multiply everything by 3. There we go. Now it looks fine, and yeah, there we go. So the only problem we have in here is that the mouse coordinates are not mapped. As you can see, you can kind of control the circle, but you're not controlling the circle precisely, which is not particularly convenient in my opinion. So I think I want to do the same thing for the mouse as well. But I don't want to repeat the same thing twice, so I'm going to create a function which is basically called remap. It takes a point in whatever coordinates you have and always remaps it to this specific resolution, right? So, and essentially what I'm doing in here, right? So I'm effectively taking this thing, divided by the current resolution, right? X and Y, and multiplied by the vec2. 900. And now what I can do, I can just take this entire thing and remap it. There we go. And now I can do the same thing for the mouse. I don't know why I'm making the same typos over and over again. And there we go. So now, regardless of the resolution, the mouse works correctly, everything scales correctly, and the mouse works correctly, everything is correct. Though I would like to maybe make the radius a little bit bigger, right? So maybe 200. Okay, there we go. So we already basically have all of the required visualization for this entire thing. I really like that. I think that's pretty cool. So let's make a small break, and after the small break I'm gonna start the explanation of how to detect that a circle intersects the rectangle. So all right, so we have some sort of a visualization in here that we can use for explanation on how to detect that those things are intersecting. So how we're gonna indicate that those things are intersecting? So I think we could basically change the color of the circle, right? So from green we can change it to red, and red will indicate that we detected that those things are intersecting, right? So let's see how we can do that. So the first step in this kind of thing is to find the closest point on the rectangle, to the center of the circle, right? So this problem is rather interesting. So if we are here, the closest point is going to be something like this. It's going to be the corner, right? If we were somewhere here, the closest point would be this thing. If we are here, the closest point is going to be this one, and so on and so forth. So we see we basically have these kind of things. Right, so how can we find the closest point in here? Well, let's actually simplify the problem by getting rid of this second dimension. Let's actually look at the problem in one dimension, right? So here we have 2 points in one dimension. So here is the left point and the right point, and the center of the circle in one dimension, right? So if we project everything to one dimension, can be in 3 different places. It could be somewhere here, right? It could be somewhere here, and it could be somewhere here, right? So, and in this particular case, the closest thing is going to be that one, right? Then in this particular case, the closest is going to be the one that happens to be the closest one, right? Actually, no. The closest is going to be the center of the circle itself, right? So in the first case, this is the closest one. In the second case, it's this the center of the circle itself, and in this case, it's the this side, right? So maybe we can even take a look at it in a different setting. So let's actually say that we have 3 cases. So here's the first one, second one, and a third one. So in all of the three cases, we have left, right, left, right, left, right. So, and the center could be here, or here, or here, right? So, and in the first case, right, in the first case, the closest point is going to be that one. Maybe I can make it a little bit brighter so we can see shit a little bit better. So it's this one. So in the second case, the closest one is this one. And in the third case, the closest one is this one. So look closer. In all of the cases, the closest point to the rectangle is always the second one. It's always the middle one, right? So 1, 2, 3, here's the middle one. In this case, also the middle one, and in this case, also the middle one. If you take 3 points here, the edges of the rectangle and the center in one dimension, the closest component, the closest thing is going to be the one that is at the center, right? And if you repeat the entire process in a second dimension, you will get the second coordinate, right? And that way you can compose the final coordinates of the closest point to the rectangle, right? So let's actually try to do that. So let's implement a function that is called closest point, right? So closest point. So it's gonna accept the center, actually. It's going to accept the rectangle, right? So we need a rectangle in here. So that means we're going to accept P1 and P2. And then we're going to accept the center, I suppose, right? And this entire thing is going to return us the closest point in here. All right. So how are we going to be implementing all of that? So we're going to start with X, right? So we have 3 values in here, P1X, P2X, and Cx. Right. Which one is the middle one in here? Right. Which one is the middle one in here? So it would be easier to just basically sort them and take the middle one, right? That would be the easiest thing to do, in fact. But they're already kind of sorted in some sense, like partially. You know for a fact that P1 is less than equal than P2, and you can kind of exploit this entire notion. So we can actually maybe mark this thing as P1 and P2, right? So let's quickly do that. So this is going to be P1 and P2. P1, P2, right? Actually, it's like X, P1, X. So this is axis. All right, so so in the first case, we can probably take the minimum. Right. If you take the minimum between P2X and the center, in the first case you would get this thing itself, right? In the second case you would get this thing itself, and in the third case you will get this thing. So I think this is roughly what we want to do in here, right? So I think we want to take the minimum between the second point and Cx. Right, it's the minimum between these things. And then we need to take the maximum between the first x and the result, right? So, and if we do that, I think we've got the right thing in here. And I wonder, so this has to be the x, right? So this has to be the x. And let's do an interesting thing. Can we try to visualize the x itself already, right? So can I return vector 2, c, like x, and cy? So we're not gonna do anything with the y coordinates, we're only gonna do it with the x. Right, so, and then I want to take the closest point, so let's actually go ahead and do that. So this is going to be a closest point, right? So this is the closest point. We provide P1 and P2 and the center, and there we go. And maybe we want to visualize that closest point on the screen as well somehow, right? If circle contains point, right? So the closest point is in here, so it's the center. The size of the point on the rectangle is going to be, let's say, like 10 pixels or something. And we do that for the current point, right? If they, you know, intersect, we're going to color this entire thing with the white color, right? So this is going to be the white color. Is it going to work? I think it is working. Look at that. Look at that. This is actually working. Look at that. This is beautiful. So we're finding the closest point to the rectangle only by x, right? And as you can see, we always sort of take this center point in here, right? We always take this center point in here, but not for y. Right, so that's roughly what we have in here. I would like to actually make these things a little bit smaller. So maybe the rectangle, I could move the rectangle somewhere. You know what? I know the resolution. I know the width and height of the resolution. So if I define something like width 1600s and height 900s, right? So, and then I just put it in here, I'll have an opportunity to just, you know, somehow procedurally like realign the entire thing. So the position of this thing is going to be, well, we also need to know the size of the rectangle, right? So let's actually call it the size. And I want to put this thing in here. So I just want to place the shapes in a more readable manner, if that makes any sense. So X is going to be positioned at effectively width divided by 2. Width divided by 2. So it's a width divided by 2, but minus size y divided by 2. And I think we have to do the same thing in here. So this is going to be height divided by 2 minus size. Well, this has to be x, I'm sorry. This has to be x and this has to be y. Right, and then we add the size and did that. Oh my god, everything is broken. Absolutely freaking broken. And I wonder why. I cannot even see what's going on in here. Yep. So vector 2, wrong operand, no operand exists, takes left-hand operand int. It's just about the ints. Okay, so this is the floats. Are you happy now? Now we're talking. So now it just tries to position it in the center. It's in the center for me, but not particularly for you, but yeah. All right, so a little bit scuffed, but I think it's all right. So the radius, let's actually make the radius a little bit smaller because I think it's too big. So now we can clearly see everything. So yeah, if I move around like that, it is kind of fine. It is kind of fine. Okay, so if we repeat this entire thing for the second coordinate, right? For the second coordinate, we will have the closest point in here. Right, so let's replace this entire stuff with y. So this is going to be y, this is going to be y, and this is going to be y. And boom, there we go. And now look at that. It actually precisely finds the closest point to the rectangle. It's just like very, very precise, right? It's extremely precise. So, and once we have the closest point, one thing we can do is when the closest point between, when the distance between the closest point and the center of the circle is less than the radius of that circle, we need to color this thing slightly differently. Okay, so here we detect that the current pixel is within or outside the circle that we're trying to draw. So if the distance between C and closest point, so it's going to be length, less or equal than the radius, we'll have to color everything with the red color, right? So that's basically the criteria in here. So this is going to be red and everything else is going to be, you know, green, right? So this is like that. So something like this. Oh my god, this editor is really annoying. I don't like it. Okay, so everything seems to be compiled. Let's take a look at it. So here it is, and boom, we are actually very precisely detecting that the circle intersects the rectangle. That's actually pretty cool. So you can use this simple criteria in your game or multimedia applications, right? So yeah, basically you need to find the closest point to the rectangle, right? And finding the closest point to the rectangle is just basically splitting the entire problem into like two different dimensions. Like it's a two-dimensional one, it's one dimension and another one dimension, and always picking the center point in here, like this with min and max. And that's how you get the point that is closest to the rectangle. And then it's just like a very trivial distance between the center and the closest point. And if it's less than the radius, there we go, you're inside. So, and you can clearly see how it works here with this specific visualization. So that's pretty much everything I wanted to talk about today. It's a very simple topic. I think it's a very interesting one, and it's very useful in, you know, in multimedia game development. I wonder if we can just make it something. Yeah, there we go. I think Shadertoy forgot to call GL viewport or something. Yeah, anyway. So I'm gonna put the link to this entire Shadertoy in the description for you to play with if you want to. So rectangle, circle, intersection, visualization, and I'm gonna put it in here. And that's pretty much everything I wanted to do today. Thanks everyone for watching, really appreciate it, and I see you on the next video. So in the next video, maybe we're gonna do something more complicated, more sophisticated. So sophisticated. Sophisticated is a very sophisticated word, not gonna lie. Love you.